what did we learn last time? So we learned that given f from omega into c, which is holomorphic, and two curves, gamma 0, gamma 1, with the same endpoints, that are homotopic, then we have that 0 f of dz. Okay, and this, as I started to say a little bit quickly at the end of last time, has many powerful consequences. The first thing to start to state them is state again what the definition of something which is simply connected. So a set omega c is called simply connected. Connected if and only if any two curves with the same endpoints same endpoint that are inside omega are homotopic. Okay, and that in the most rough, in the crudest sense, just means that the thing doesn't have any holes. So if we have a donut shape like this, then there's no way that these two curves are homotopic. We just can't deform one smoothly onto the other without ever leaving the set or having some kind of discontinuity. Yeah? But if you don't have that, then you're in good shape, right? So if you have a set like this, if you have a set like this, a set of a simply connected set. Because if we have any two curves inside this with the same endpoints, we can indeed smoothly deform one onto the other. Yeah? So, for things like this, we can now do the general theorems of complex analysis. Previously, we've been carefully talking about sets that are delta good, which meant that if we took a collection of squares I, so previously we had we said omega was delta good, no dyadic good. If omega was the union of a bunch of squares of some size, qi, where if we considered the union of all these guys that weren't inside this thing, qi, then this is connected and unbounded. And all this does is it just prevents you having a set which contains something in its interior, like a hole, right? So this is a crude way of saying you have a set that doesn't have a hole. Yeah? So these things are simply connected sets. But now with this notion of homotopy, we don't have to define it this way. We can define it in a more subtle and more general way. And the point about this is that all the stuff that was true previously for this dyadic good sets are now true for simply connected sets. So the main theorem is that suppose, oh, should I put the theorem right up here? Theorem. F is holomorphic on a simply connected set. Then F has a primitive. i.e. for every, i.e. F prime is equal to F omega. Okay, so I'm going to erase the board. In the meantime, you think about how we can prove this. So what did we prove before? It was a homework exercise for you. We proved that if we have a dyadic good set, then this was true, right? And what was the main steps to do that? What was the main thing we had to think about to be able to achieve that? Yeah? Think about that, and then tell me why it's actually true if we're simply connected. Okay, so proof. Why is this true? Yep, exactly. So if we pick any point we like, say z0, yeah, then we're going to define L of z to be a path that connects z0 to z, wherever z is. So like this, right? So this will be L of z. Yeah? And this is obviously not unique. We can have different path that does this job. Maybe this path is a little bit exciting. It does this. Right? We can have a different path, yeah? But these paths, by definition, are homotopic. They're homotopic if we can smoothly define one to the other, yeah? Which by the previous theorem means that any integral we define on these paths will be the same. Yeah? So pick z0 inside our set omega, and let L of z be any path that starts at z0 and ends at z. And then define capital F of z to be this thing, to be the integral of L of z of little f of w dw. Okay? So, by the previous theorem, this is well defined. It does not depend on a particular choice of path L. Okay, so we at least have a well-defined function. All right, someone else. How do we go forward? How is this helpful? Why is it the case that this thing is going to be the antiderivative? Let's blow up what happens here. Okay. Let's blow up to this big picture. So this is Z, this is our path coming in like this, yeah? So why is it the case that capital F is the primitive of little f? Okay, let's see what happens if we move off little z by a little bit. Suppose we move up here. This is z plus h for some small number. Yeah? So capital F is the same. Well, capital F of z plus h is what happens when we take any path that goes in and reaches z plus h, right? Yeah? So it's the same for any path that does this, right? Yeah? And what we're going to be considering, of course, since we want to find the derivative, so we consider capital F of z plus h minus capital F of z, yeah? And we're hoping that when we divide this by h, it's going to tend more and more to just little f, right? Okay, now look at this. Look at this and look at the picture. What is this on this picture? Right. Yeah, because it is true no matter what path comes to reach z plus h, right? It doesn't have to be this one, and it's most convenient if it isn't this one. Let's take the path that exactly follows the path that went to z, and let's just extend it up in a straight line up to h, right? So let's take the path that goes up like this, like this. Yeah? And by the theorem, this is a perfectly good path, right? This thing does it, yeah? So when we look at this thing, yeah, all this becomes is just the integral over this line segment, z to z plus h of little f of w dw, right? Previously, we did this by applying Cauchy's theorem on a triangle over and over again, but now we have a more direct thing to do, yeah? Everybody with me here? All right. Now, why does this make you so happy? Why is everybody jumping up and down? All right. If we just look at this expression, yeah, this is just given by this. Over h, right? And this thing, as we look at this expression pretty closely, look at this. If we look at integral of z plus h of f of w dz, let's subtract from that just, say, f of z times h itself, like this. Then what is this? This thing is the same as this. Yeah? So put up some value signs around this. Yeah? and then this is less than or equal to this thing. Right? And then this thing gets very small because f is continuous. Yeah? And we're just going on this little tiny interval of length h, right? So this is less than just the length of this path, h, times the supremum over this interval z plus h of f minus f of z. So when we take this expression minus f of z, so capital F of z plus h minus capital F of z over h, minus just f of z itself, right? So it's going to be this thing minus just z. So if we divide h through this expression right here, we have exactly what we want, and then this h here will just vanish over on this side, right? So this thing is less than just the supremum of f minus f of z over this little strip right here, which will go down to 0 as h goes down to 0. Yeah? Everybody with me? And that's the same thing we did before, right? So this part of the argument when it's the same thing after we've reduced it down to going up this straight line segment by using Cauchy's theorem on a triangle, right? So once we're in a little tiny ball, then it's an entirely local argument, and it doesn't notice whether we are in a simply connected domain or a dyadic good domain or anything, right? So this part is exactly the same argument. The only part which was new, the only part was different, was that now we have the right to define this in a well-defined way, no matter what z we have inside our simply connected domain. And the key point is simply connected is a wider class of functions. A wider class of domains. Yeah? Cool. So this is not particularly hard. It's essentially just using the definition of simply connectedness and the main theorem we defined before, which allows us to define this. But then this has all the cool consequences that we garner, right? So for any simple closed curve, gamma in a simply connected domain omega we have that the integral of gamma f of z dz equals 0 for any holomorphic function, right? Because we have a primitive, yeah? Cool. So if we have that, we also have Cauchy's integral formula, right? Cauchy's integral formula for any closed curve inside a simply connected set. Yeah? So all the stuff where we had to be careful about stuff, we don't have to be. Okay, perhaps the most dramatic illustration of the power of this is that we can now define the complex log on a much more general class of domains. So recall, we defined the principal log which were like this, as follows. It's log to the base e, which just means the real log, the log on the real numbers of the absolute value, plus I, and then the principal argument of z, where the principal argument is inside this range minus pi to pi, right? And when we do this, then we have a perfectly good, well-defined function on the complex plane. Take away the negative real numbers. So defined and holomorphic on the complex numbers, take away this thing. So this means the negative real numbers, right? Because we have an issue when we go all the way around. So this is 0. So when we go all the way around, then we can't cross this because we have a discontinuity, because the principal argument goes from pi to minus pi here. So it's not holomorphic on the entire complex plane, but on this slit domain, it's holomorphic, right? So previously had to be somewhat careful when we did anything to do with log, that what log we were talking about firstly, and that we don't go over the place where there's some kind of discontinuity. But now we have the possibility to define a much more general log. So theorem, given any simply connected domain, I'll put that over there. Omega, we can define, which has some properties, that contains one but does not contain 0. We can define complex log, which is depending on this particular domain. So I'm going to write log of omega of z such that the following is true. So 1, this is a holomorphic function. On omega and d by dz of is 1 over z. Second property, e to the z, because it is indeed an inverse to the exponential function. And the third property, so this is how Stein words it, but later I'm going to ask you exactly what he means by this. So near, or for real numbers, so when it's a real number, then it is just equal to the natural log that we know from calculus. Okay? All right, proof. I should put it here. Proof. All right, so what is the big deal about having a simply connected domain? It's that we can have any two paths with the same endpoints being homotopic, and therefore have the same integral. Yeah. Since we are excluding 0, the function 1 over z is a nicely holomorphic function on our domain. Yeah. So let's define log of omega. Actually, I'm going to write f of z because it's just easier to write this, and later I'm going to say f of z is this log omega of z. So define this to be the integral of L of, where do we want to start? We want to start from 1. So L of z of 1 over z dz, where L of z is any path from 1 and ending in z. Yeah. So this is well defined. Yeah. And the first property, that d by dz of f of z is equal to 1 over z, is exactly the same argument we did before. It's exactly the same argument. Yeah? Because we just define up to z like this, and then we have this z plus h, right? So then f, maybe for consistency I should have written capital F. Let me write capital F, because that's what I used for the primitive before. Then capital F of z plus h minus capital F of z is just this integral over this little line segment of 1 over z. Oh, 1 over w, since we've picked z. Right? So exactly the same argument will give you this thing. Everybody happy with that? Yeah? Okay, good. So, this we believe, point 1 is not difficult. Yeah, point 1 is not difficult. Okay, point 2. Point 2, we want to show this. So, now, for I. So, it's equivalent to showing this. So, equivalent to showing that z to the minus 1 e to the, and we're calling it capital F, right? Capital F of z is equal to 1. Right? If we can show that, then that's the same as this. Yeah? Right, so we're going to show that by differentiation. So, first thing we're going to do is show that when we differentiate this expression here, it's going to be a constant. So look at this. So we do this thing. Maybe I want to do it the other way around. I do want to do it. I'd rather differentiate e to the minus f. This thing is also the same as this thing, by the same reasons. Yeah? So let's make our differentiation life easier. If we differentiate this thing, what happens? Then by the product rule, we just have e to the minus f of z plus z e to the minus f of z, and then minus f prime of z. Right? And f prime of z we've seen is 1 over z, so then that thing just becomes e to the minus f of z minus e to the minus f of z, which is 0. Yeah? Cool. So the derivative of this thing is 0, right? and it's defined holomorphic on a simply connected set. Yeah, therefore the entire thing is constant. The entire thing is constant. And the only thing is to show that this thing is actually equal to 1. When we show it's equal to 1, then we're done. Yeah? But if we stick in the value z equals 1, so at z equals 1, what happens? We have 1 e to the minus f of 1. What is f of 1? What is f of 1? Someone who hasn't spoken yet. What is f of 1? Look at the definition. What is f of 1? It's 0. Yeah? So then this is just 1 times e to the 0, which is 1. And therefore, that is what this constant is equal to. Right? So we've shown that this thing is a constant function, and that constant has to equal 1, just by sticking in z equals 1. Yeah? And therefore, this is shown, this is proved, which is proving this. Yeah? Cool. Everybody happy. All right, so we've proved 1, we've proved 2, now we're going to prove 3. I'm going to raise the board, think about how to prove 3, and I'm really interested to hear from someone who hasn't spoken yet. Okay, so point 3. The claim was that this complex log we've defined on the real line near 1 is actually equal to just the standard log that we know. Yeah? Okay, tell me why. And you have the right to take near to be as near as you want. So near can mean anything at this point, and then we'll think about what it actually means. So tell me why. I mean, how did we define our thing, right? How did we define it? We defined capital F of z to be the integral of L of z 1 over z dz. Yeah? So our path could well be just on the real line, right? So if this is 1 right here, yeah, then since it's an open set, there is some ball which is entirely contained inside omega, yeah? And then for any number on the real line inside this ball, we can indeed take our path to be just a straight line going towards it, right? Yeah? Okay, and then keep going. So what's the consequence of that? Yeah. F of z is exactly, this is exactly the definition of, let's write it like this, dx. Let's write it like this. This is exactly the definition of the natural log, right? This is how we define natural log, yeah? Which is the natural log. Okay. Cool. All right, so example. Let's put 0 here. Let's put 1 here. And then let's take this thing. And let's do this. Okay. So this is the real line. Yeah. And let's fill this out so that we see what we're talking about. So according to our theorem, this guy right here has a complex log, a well-defined holomorphic function, which is a complex log. So take omega as shown. It is simply connected. So we can define a complex log all right. So what's going to happen to this guy? Well, if we just do this thing that we did before, when we just figure out what complex log has to be, so the most general form of complex log, so general form of log of z is log of z is equal to log to the base e mod this plus where arg is this multi-valued function, right? So, oops, there's an I here. Arg of z is equal to the principal argument plus 2 pi k for any k belonging to this thing, right? This is what we figured out when we discussed what complex log has to be, right? And the issue is we don't like it like this because this is not a single valued function, right? Yeah. But the claim is now we do have a single valued function, right? Yeah, on this thing. Yeah. Okay. All right. So around one itself is pretty clear, right? What about here? What will the value be around here? So there's no way for you to tell me, what the length this is. So tell me about the imaginary part of complex log, depending on this domain. What will the imaginary part be here? Just here. What will it be here? Given that on the real line, we have this just equal to the standard thing. So the complex part is 0 here on the real line. What will it be here? Come on, this can't be high. No. What is the argument of a complex number around here? It's pi, because we're going anti-clockwise, yeah? Yeah? So it has to be equal to something very close to pi, right, as we approach this thing. And previously we had to be careful, because on this line we had a singularity, but now we don't. So actually when we're on the line, it is still perfectly fine. It's a holomorphic function, it's continuous, therefore it actually has to be equal to pi on the line, yeah? Okay, what about if we move a little bit down? What's it got to be? Well, it still has to satisfy this, right? It still has to satisfy this, because that's just what happens when we just differentiate stuff, right? So what does our complex log have to have for its imaginary part if we move down a little bit below this line? Well, if it was negative pi, then there'd be an issue, right? What would the issue be? Can we just continuous? Right. So it can't be negative pi. Yeah? So what else could it be? I mean, it has to be some value inside this set, right? Because that's what we know. So which one does it have to be? Louder? No? If we had 3 pi, what would we do? We'd go, this is pi. If we had another 2 pi, then we'd go all the way around again to the other side. Right? So we are just a little bit below the real numbers. Right? So if we had 3 pi, we'd actually just be on the real numbers itself. Yeah? Pi plus something. What something? You don't have to tell me exactly what the something is, just tell me about the something. Yeah, pi plus a little something, right? It has to be pi plus a little something. Because it's a holomorphic function, it's continuous, right? Yeah? So the argument, or the imaginary part of this thing always has to belong to this set, right? Always has to belong to this set. Yeah? Yeah. But the only way that's possible, and for it to remain continuous, is that as we move from here down a little bit, then we just increase the angle by a little bit. Yeah? Cool. All right. So that's what happens there. Yeah? And we're going round and round and round and round and round and round and round. What is going to be the imaginary part of our complex log right here? Two pi, right? Because this argument, this imaginary part is changing continuously, right? So we go from 0, pi, a bit beyond pi, yeah. And at every point, it is just the argument of the z. It is one of these values here, but it has to change continuously, no? It has to change continuously, and the only continuous choice of the argument of z as we move around like this is to go like this, and then out here at 2 pi. Yeah? Cool. All right, what do we have when we move a little bit up like this? What do we have now? Yeah, 2 pi plus a little something. Yeah? And as we move around like this, like this, like this, like this, like this, where are we here? What are we here? What is the imaginary part of our complex log when we're here? Someone else. It's 3 pi, right? What about here? What about when we're here? What is it now? 4 pi. What about here? So I'm going to write some of this stuff down now. Let's go. It is indeed also 4 pi. Tell me why. Tell me why. Right. So the argument is continuously changing, right? Yeah. And has to go back to this thing, right? Has to go back to this thing. Yeah. There's no way it could do a whole 2 pi because we don't do 2 pi loop in the argument here. We're only going up a little bit and down, right? And then this thing again has to be 4 pi. Yeah? But even if we did go all the way up and down, it still would be okay because we reverse that. So if we had something like this, oh, damn it. This thing here would still have its imaginary part be 4 pi because we've gone all the way up here, right? And now we're going to have 5 pi, but then we're going back, and now we're going back to 4 pi. Yeah? Cool. Yeah? So now we have, say it louder. Yeah. 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 Just think of this as for any z inside here, you have to continuously define this angle, okay? You have to continuously define this angle. But you have the right to take it over the entire real numbers, right? You're no longer restricted to minus pi to pi or anything. You can go anywhere you want. So indeed, as you go like this, then yes, you're gonna take another value of 2 pi every time you go counterclockwise, and then you unwrap it going clockwise like this. Yeah? Cool. So we have much more freedom, much more power in our ability to define a complex log. Yeah? We can define complex logs now on any domain that excludes 0, which we want to exclude because then there's going to be a singularity there, so it won't be holomorphic. We want to include 1 just because it's convenient to include 1, so we can take that as a starting point and have something which is consistent with the ordinary log on real numbers. Yeah? Okay, now answer this question about what does Stein mean by numbers near 1, which we have that this is true. In what sense is this true for numbers near 1? Previously, we showed it was true if we have a small ball around here, right? Tell me precisely when is it true. I mean, think about the argument we did here. Think about this example. Okay, so you claim it's true here. Yeah? Does everybody agree? Yeah, and indeed it is true here because this argument works fine here, right? Yeah. If we just take the connected interval on the real numbers that contains 1, right? That is, let me say that more completely. If we intersect the real numbers with our set, we're just going to get an open set on the real line, yeah, which is made up of the union of intervals. We'll take the connected interval that contains 1, yeah, and then that thing we can do exactly this argument on, and then on this interval here we are fine. Okay, now the second part of the question, what about other parts where we wrap back, where we wrap back and then hit this thing here? What about this thing? Is it true here? Definitely not true. It's definitely not true. Yeah? What about this thing? Is it true here? Definitely not true. Now let's think about Laura's suggestion. What about if we have a little interval like this, and then we can do some funny stuff, whatever, but then we go around and we go back like this. So this is 1, 0 is out here. We know it's true here. Is it also true here? Yeah. Yeah, it's also true here. It's also true here. Yeah. Cool. So the answer is a bit more subtle than just numbers near 1. And the only kind of general formulation you could do for any set would be to say, take the open interval, which is given by the one connected component of the real numbers intersected with your set that contains 1. Then that thing for sure we have this representation, yeah? Because we can't guarantee whether we have something that wraps back around like this, or if it goes around like this. I mean, we could maybe try and formulate something. It'd be pretty hard to formulate this. Well, maybe not. maybe not. Maybe not. Indeed, maybe as you say, we could just formulate this as saying this is all the points where the imaginary part of the complex log is equal to 0. Yeah, okay. Yeah, okay. So yeah, we could do something better. All right, cool. So this is complex log. And now we have it in a much wider class of domains. We're going to use it for some stuff. The reason I say that is I'm going to connect this to number theory shortly. So given that we can now, a more general log, we can define complex powers. So we've done all kinds of things with complex numbers. We've multiplied them, we've added them, whatever. But I haven't talked about when we try and take things to a complex power. Right? But we can actually do this. So given z and alpha, which are complex numbers, we define z to the alpha to be equal to e to the alpha log of z. Okay? And if we do this inside a simply connected domain, then log of z is a well-defined holomorphic function. So this thing is a nicely well-defined function. It makes sense itself. Yeah? So if z is restricted to a simply connected set, a simply connected domain, that contains 1 and doesn't contain 0, then well-defined holomorphic function. And let's just make sure that we believe that this is a reasonable definition. So if z and alpha are both real, then this gives us exactly powers as we know them on the real numbers, right? Nothing surprising here. If we take z belonging to the complex numbers, and let's take some integer n, then let's look at what this is. So typically, the nth root of a complex number you know as these n different complex numbers, right? All spaced equally around a unit circle, or not unit circle, but a circle of radius, the nth root of absolute value of z. But now, what does our definition give? Then this thing should be e to the 1 over n log of z, like this. Yeah, and this thing is a holomorphic function. It's a well-defined function. Yeah, this is a well-defined function. So we're no longer with this way of defining powers, creating multiple roots. We're creating one. You know, this is any alpha. This is any complex alpha. This is a well-defined function. So our previous understanding of roots now changes. We now have one root. Yeah? And let's see what happens when we do z to the 1 over n to the n, then this is just e to the n over n log of z, which is just z, so it does what we expect it to do. Yeah? Yeah? Cool. So if we have our example we had before, the curly snake thing, right? So this is 1. This is 1, and this is 0. All right, so tell me about what the nth root of z will be on this thing. Tell me about this. Tell me about the imaginary part of the nth root of z when z is here. So this is the real line. Suppose z is here. Tell me about the imaginary part of the nth root of z. Well, we can sort of reason the way we did before, right? So in general, what is this thing? Oops, there's one end. Is equal to, and then it's going to be e to the I, the argument of z plus 2 pi k over n. And we run the k over all the numbers, and then we end up, there's just n distinct things that come out from this thing. Yeah? Yeah? So what this function is doing, what this root power is doing now with this definition of complex powers, it's picking out a continuous guy from this collection. Right? It's picking out a continuous guy from this collection. Yeah? Cool. So let me express what I want to ask better. So when we are here, which guy is it picking from this thing here? Which guy is it picking from this thing here? K equals 0, so what will be inside here? So it's a root power, right? So this is our z. Yeah. So z goes to z to the 1 over n. Yeah? Yeah. So what this will do, it'll just take this pi divided by n. So this guy gets like taken back over here, right? The angle is divided by n. Yeah? Yeah? And if we move a little bit down, the same thing happens. Yeah? Yeah? So we can just continuously choose this argument as we did before. So we go 0, pi plus something, 2 pi plus something, 3 pi. Yeah? And what's happening here is we're taking that continuous choice of argument and just dividing it by n. Yeah? And that's how we form this well-defined, one-valued root. Yeah? So once you can continuously choose the argument, then continuously choosing a root power is kind of follows easily from it. Yeah? So the fact that we have a well-defined, one-valued root on a simply connected domain follows from a similar kind of reasoning. Do you see what I mean? Yeah, give me a thumbs up if that makes sense. Laura, is that clear to you? Okay. Okay. Let's look at it more closely. So if we start here just on a real line, then the root is just the real root. Nothing changes. Yeah? And if we take any z like this, right, the nth root has to be one of these numbers for some k. Yeah? Yeah? But it's a holomorphic function, so we're continuously choosing it. Yeah? We're continuously choosing it. Yeah? So what is difficult about this thing is that it's got this singularity here. The principle has a singularity here. When we add this 2 pi k, then there's no singularity because it's all the same thing. Like when we add all possible multiples of 2 pi k, right? But we don't have an issue if we are allowed to take the argument to just increase beyond pi into pi plus something, and then even more to increase beyond 2 pi into 2 pi plus something. Yeah. Yeah. So what we did when we looked at this example with complex log, we found that we could just continuously choose the argument, right? Because complex log is kind of easy, right? So complex log in its general form is like this. And all we did was we noticed that we can just continuously choose one of these guys here in this multi-valued set in a consistent way, continuous consistent way, such that this log that we define depending on our domain becomes a holomorphic function. Yeah? So the real power is being able to continuously choose this choice of argument. Okay, so now what we're going to do is we are going to stick in that continuous choice of argument into this thing. Yeah? And let's just fix k to be equal to 0. Right? So let me write it this way. Let me write arg omega is the continuous choice of omega. This is the continuous choice of arg. So for complex log omega of z, then it is equal to log to the base e of absolute value of z, and then this smart choice like this. That's what it's equal to. Yeah? So we have this function from z into the real numbers, which is a nicely continuous function, such that this is always true. Yeah? So that defines this thing. Are you with me here? Yeah? All right, so let's do this. Let's just define this thing to be like this. To be the argument of omega of z over k. That still is inside the previous set that we had there, right? But it's just one choice of it. Yeah? Yeah? So not only general, so we'll define now. So now we're going to define. So since this argument function here over k, it definitely belongs to the thing we had before, which was the general expression like this. So the principal argument plus 2 pi k over when I'm saying k, I should have been saying n, sorry. Typical nonsense, there we go. This guy definitely belongs to this set, right? Yeah? Yeah? Cool. So if we define it this way, it will be one of the choices of the nth roots that we have in the general formulation. Yeah? It will be one of them. Yeah? But it'll be a continuous choice because this is a continuous function. Yeah? Cool. So when we have a z like this, then the argument will just be divided by n. Yeah, so it'll be taken to here and then shifted back somewhere over here. Yeah? And if we did this looping around n times, and then we took the nth root of this guy, then that guy would be someone over here. Yeah? So think of the action of this. Think of the action of this nth root as taking this spiral and then unspiraling it, right? So if n is, so how many times are we spiraling around? We're spiraling around like 1.5 times, right? So assuming n is bigger than 2, then the action of this complex root is of this nth root of the complex number takes this spiral and it'll kind of unwrap it into some kind of like shape like this. It'll unwrap it. Yeah? See what I mean? Which is the kind of thing it should do, right? Because what's the nth root? It should be undoing z to the n. What does z to the n do? It takes something and wraps the complex plane around itself n times, right? So we should expect that the nth root unwraps it. Yeah. Cool. All right. So we have a nicely defined complex power, right? A nicely defined complex power, and we can understand what the nth root is as a single valued function as a consequence. Yeah. Yeah. Cool. I feel like I'm out of time, but I want to talk a little bit more about. So I'm going to talk a little bit about the applications to number theory. Some of you have to go. This is just for general interest. So you're not skipping anything. So go whenever you have to go. Anybody go whenever you want to go. But I just want to add this briefly because it's interesting. We can define the following function, zeta of s, to be the sum from n equals 1 to infinity, 1 over n to the s. This is called the zeta function. And it turns out that this thing converges whenever the real part of s is bigger than 1. So this is defined on omega of z such that z is bigger than 1. So here I'm cheating a little bit because previously I said we have to include 1. And here I'm excluding 1. Not this. Oh, the real part of this. But this is a minor technical thing. This is a simply connected set, clearly, and we could just make a little bump and include 1 itself, or we just start from 1 and take paths starting from 1. So ignoring this technicality a little bit, this complex power n to the s for any s inside this thing is a well-defined thing because we have our log well-defined in the set, and therefore complex powers are well-defined. So it's a well-defined function on this region, and I claim it actually converges and gives you an answer. And why so? Well, if we look at this, so if we take the absolute value of s to the n, what's this? This is absolute value of e s log of n, which is the absolute value of the real part of s plus the I times the imaginary part of s times this thing, log of n. And then this thing, we break this up, and then this is just the absolute value of the real part of s log of n, which is just n to the real part of s. Yeah? So the series converges absolutely. So series absolutely for s belonging to omega, and therefore it converges by a simple thing. So it defines a Cauchy sequence, we can take the limit, blah, blah, blah. Yeah? So this is a well-defined complex function. It's the well-defined function on the complex plane. Yeah? Yeah? Cool. And we've learned that power, this is the power series, but okay. It turns out that this is indeed holomorphic, and that requires a little bit of work, but not that much work. If you have any finite sum, then you can believe that it's holomorphic. And the fact that it's converging absolutely means the tail end is not going to create a problem by arguments very similar to how we showed that power series were differentiable. So this is holomorphic here. So holomorphic on omega. And it turns out we can extend it. So we have this thing I talked about before briefly of analytic continuation, that if we have a holomorphic function defined on some region, and we can find some other region that contains that region which agrees with that holomorphic function, then that's a unique extension of it, because if it wasn't, then we would have some region where the bigger holomorphic function was 0. So what I mean is this. If we have some u here where we have a holomorphic function, and then some v outside here where there's a holomorphic function defined on v which agrees with the one on u, then that is the unique extension of it. You know, because if that wasn't true, we would have two different holomorphic functions with different extensions on v, and then we take the difference and would have a function which is 0 on u but non-trivial on v, and that's not possible for a non-trivial holomorphic function. Yeah, it's analytic continuation, right? So it turns out we can uniquely analytic continue this guy to everywhere, except it has a pole at 1. It has a pole at 1 itself, which is not a surprise because we put s equals 1 here, then this is a divergent series, it's a harmonic series. Okay, so this actually can be continued to be a meromorphic function. So can be I don't know how to spell this word. Continued to a meromorphic function on the entire complex plane with the pole at 1. Yeah? So I once, a long time ago, as a postdoc in Oxford, and one of my office mates was taking a physics course, and he came back from the physics course and announced that the sum from n equals 1 to infinity of n was equal to minus 1 over 12. And what he meant by that was that if you analytically continue this guy to its function, meromorphic function defined in the entire complex plane, i.e. zeta of minus 1 happens to be minus 1 over 2. Yeah? So if you stick in minus 1 into this expression, you do indeed get this thing, yeah? Which is, I mean, this is not true. This is obviously false, as you people know. But as a kind of a joke, you can somehow claim this is a consequence of this thing. So this is of interest in physics as well for numerous reasons. But this first was in interest because of number theory. And it was used to prove the prime number theorem. Which is the following. So if you let pi of x equal the number of number of pi's, the number of primes less than x, then this thing has a particularly neat distribution. Then the limit as x tends to infinity of pi of x over x divided by natural log of x is equal to 1. So that means that the number of primes in the real line on the natural numbers is actually growing surprisingly fast. I mean, it's, as you know, it's infinite, right? But this says something about how it's growing, because what is this function? Well, x over log of x is just being flattened slowly by log of x, right? Yeah. So if this wasn't this, if this was just whatever, this is like almost the slowest thing you could do to slowly bend the function y equals x, right? Yeah. If this wasn't this, then if it was like if this was just x over 2, then it would say that you have a 50% chance of having a prime number if you pick any numbers from 1 to n for very large n, right? Which would be insane. That'd be a lot of prime numbers. But this says that they're actually it's not that much worse in a sense. So there's fewer and fewer prime numbers as we go up towards infinity, but they're not getting scarcer as quickly as you might expect. They're only slightly getting spread out. And proving this was a huge deal back in the day. It was proved by Hadamard and Valdepussin, I think, in I don't know. I'm just making a guess, but a long time ago. And 50 years before then, some guy called Chebyshev, I think, proved a weaker version of this where he had upper and lower bounds. So not the limit was 1, but just it was less than something and bigger than something for all large enough x, just with elementary methods. And this follows from this stuff, from understanding the behavior of this particular complex function, this meromorphic function, very carefully. And $1 million prize is to prove the Riemann Zeta conjecture, which is the conjecture that the only zeros of this thing that are not along these numbers like this are negative even numbers. So these are called the trivial zeros for some reason. So there are zeros of this thing along these numbers. Oops. And there are a couple of, or there are zeros, not a couple, there are many zeros along on the line given by real numbers of z equals 1/2. Okay, so those are the only places where zeros are known, and the conjecture is that the only zeros are those ones and the ones that live on this line when the real number is 1/2. And if that can be proved, then the whole math of consequences follows, including a much sharper result about the distribution of primes as x goes to infinity. So be a dramatic improvement on this if that could be done. So this is a problem many people have studied, and this was the hottest stuff around in the 19th century. It was very surprising and shocking to them that they could study this meromorphic function and then learn something about this thing, which is seems a completely different thing. It's the distribution of primes, it's totally discrete kind of question. But it turns out you can. And it was even more shocking to them that if they could prove this, then they have a much stronger result. So many people have tried to prove this, and that's your homework for next week. All right. So yeah, that's enough number theory background. I will see you all on Tuesday, which is our exam day. So please start to review for the exam. I have office hour on Monday, but you can just email me if you have any questions, and I'll see you all then. All right. Bye-bye, people.